In the early 60s, maybe you were back from MIT, you were in Chicago.
Yeah, and I'm about to go to Princeton.
Yeah.
So I come to Princeton, I have to say, partly because Ellie wanted to go to Princeton. I did not want to leave Chicago. I was very happy in Chicago. I had been an undergraduate and then a graduate student. I came back on the faculty. Everything around, there was Calderon and Zygmunt and other people. But Ellie, I think, rightly thought that Princeton was a nicer place to live, and we had small kids, sure, babies. So the first year was the academic year 62, 63. I was on leave from Chicago. I was at the Institute. And at the Institute, there was this atmosphere that emanated that I felt was very unfriendly from point of view of analysis. I mean, it was, cohomology, functoriality. I mean, that's what you had to know, that was the language you had to speak in, or maybe some number theory, but analysis was sort of advanced calculus. So that was very unfriendly. And it sort of permeated a little bit into the university too, because I mean, the senior people at that time at Princeton were Bachner and Feller, and they were not so active anymore. And of course, there were the younger people. Hugo Rossi had been, he left just the year before I came. Also Don Spencer left the year before I came. But there were other younger people, but it wasn't the same, the weight of, the weight that I felt of sort of being isolated as an analyst. There was Ed Nelson and Bob Gunning, and there was David Laudenslager too, who passed away within a year. Things didn't change for me until I began to have students, particularly you, Charlie, that began to change the atmosphere of analysis.
You changed the atmosphere.
No, but I mean, it made a great difference. Another thing that made a great difference was that about that time that you were my student, that's the time that Don Spencer and Joe Cohn came back. And Don Spencer was a very nice guy. I didn't have much really mathematical interchange. With Joe Cohn, I think it was more important. My first year, I think it was, when I was in Princeton, Joe Cohn was at Brandeis at that time, and he came to give a lecture. And I think he was lecturing about work that he had done with Hugo Rossi. Anyway, it was about D bar B. I didn't understand very much about D bar B. I didn't know anything about several complex variables, I have to say, because where I was brought up, one didn't mention it, it didn't exist. One complex variable, yes, but several complex variables, nothing. But he said something which struck me. It seemed that in several complex variables, as opposed to one complex variable, if you have a holomorphic function and you look at its boundary values, which of course, for a harmonic analyst, this is what you want to do. You can characterize those functions by the fact that they are solutions of differential equations. And that is totally unheard of in one variable. So that was one thing that struck me greatly. Another thing that struck me, I think it was about a year later or 2 years later, when Joe Cohn came. And of course, there was the D bar Neumann problem. Again, I didn't know anything about the D bar Neumann problem, enough to know that it was some kind of a boundary value problem. And he said to me that he wanted to apply the theory of pseudo-differential operators to this boundary value. Of course, theory of pseudo-differential operators was, of course, closely related to the theory of singular integral operators, but it had been put in a form which was very good for PDE by Joe Cohn and Nirenberg, and worked out, also generalized by Homander. So there was this theory of pseudo-differential operators, and how do you apply this theory? The question was, how do you apply this theory of pseudo-differential operators to solve the D bar Neumann problem? And Joe said he had tried several times and it didn't seem to work. All right, so now I want to connect with a different strand of interest. So as I said, I had been interested in semi-simple Lie groups, which I had worked with Ray Kunze. But then after a while, I started to work with Tony Knapp on the subject. And we started to look at the totality of semi-simple Lie groups, even those of rank 1. And among them was the group SUN1. And the group SUN1, the basic nilpotent group associated with it was the Heisenberg group, in the same way as for SON1, the Euclidean thing. Now we are in the 70s or the late 60s. One had to prove that certain operators were unitary. So maybe I will come to that story in a moment. That was the challenge. But anyway, I had learned about the Heisenberg group. And I realized that one could not do pseudo-differential operators, which was like Rn, but one had to do the class of operators which were like the operators on the Heisenberg group with their own kind of dilation structures, that those were the right operators. And that started off with work with Folland, and that turned out to be very successful. But I want to come back to just one other strand of this, which was what's called Cutlar's lemma. So Cutlar was a graduate student, a somewhat older graduate student. He had already worked on many things in mathematics, of Zygmunt. And he came to visit Chicago at the time I was a graduate student. I don't remember exactly when, but he had already gotten his degree. And one of the very striking things that Cutlar had done was Cutlar's lemma, which was a proof of the boundedness on L2 of, let's say, the Hilbert transform without the use of the Fourier transform. And it was a nice decomposition of the operator into different dyadic pieces which almost commute and satisfy some orthogonality principle. And then at some time in the middle 60s, there's a whole interesting strand of mathematical development. Calderon had been working on what was then later known as the Calderon commutator theorem. And that developed into the proof of the Calderon's version of the Cauchy integral and all that great development that took place. But in this commutator theorem, the basic fact was to prove that there is some operator, you want to prove that it's bounded on L2. And it's not your usual convolution operator. And of course, that L2 is the key point here. So you need to have an L, because once you know how to prove that it's proved in L2, then by what's called the Calderon-Zygmunt paradigm, it's bounded in LP. So Calderon had a very nice, ingenious argument, but it was very special to this operator. And so I was thinking, maybe there is a general sort of L2 theorem that can be used to prove that that operator is bounded on L2. So what could that L2 theorem be? And so I remembered Cutlar's lemma. The only problem was that Cutlar's lemma was the operators in question basically had to be abelian. They had to commute. And one way to see Cutlar's lemma, even though he had a very complicated proof originally, is by simultaneously diagonalizing these operators, and then it's quite easy. So I thought to myself that if only one could find a non-commutative analog of Cutlar's lemma, then one could do this Calderon commutator theorem. It just so happened that at that time Cutlar had he spent a few years in the United States, and he had a position in Rutgers. And one day, I think I went to Rutgers for whatever reason, either to talk to him or we met. And I said, Misha, you know, your nice theorem. You know, I think there is a non-commutative analog. And if that non-commutative analog holds, then I think we can prove the Calderon commutator theorem. So that was our conversation. And then I went home, and like in many of these things, when you talk to somebody else about some idea you may or may not have, just by talking about it, you think about it. And I thought about it, and I realized how to prove the theorem. And I was very excited, and I was going to tell Cutler, but Cutler called me up and he told me he had also found the proof. So we had both found essentially the same proof at the same time. But before I talked to Cutler about it, I tried to use it to prove the Calderon commutator theorem, and he had also tried it, and we both failed. Okay, the upshot of the story is that a number of years later, David and Journet proved the T of 1 theorem. So the thing we were missing, they found, and they used this argument together with, and the T of 1 theorem then gave a quick proof for that thing. And of course, that was very important in other developments.